If I have two wave sources, one blue and one red, that happen to have the exact same frequency, when I line them up together, they always produce constructive interference. Here you can see a crest aligning with the crest, and it creates a supercrest. Here you see a trough aligning with a trough, and it creates a super trough. And when you play that sound, you hear just a single tone. But let's say these two source frequencies were ever so slightly different. Now that the red wave has a slightly higher frequency, that means it has a lower wavelength. At this point, we have constructive interference just like we did before. However, because blue has a higher wavelength, it eventually stretches out ahead of the red wave. If you zoom out, you can eventually see that these two waves experience destructive interference, where the crest of the red is meeting the trough of the blue, and vice versa. That causes the amplitudes to subtract from each other. What you ultimately end up with is a series of packets called envelopes. And the sound now comes in, well, waves. You hear a loud sound, then it gets quieter, then louder, then quieter, as the waves shift from constructive to destructive interference. That can happen pretty quickly. Currently, I have the two frequencies differing by 15 Hertz. If I went any more than that, the human ear wouldn't really be able to distinguish how quickly this is happening, and you'd start to just hear two separate notes. If the frequencies are more similar to each other, say 255 and 250, then it takes a little bit longer for them to get out of phase and back into phase. What you heard the first time was a beat frequency of 15 Hertz. That meant it was going from loud to loud again 15 times every second. When I decreased the frequency of the red wave, they only differed by 5 Hertz. That meant it went from loud to loud only 5 times every second, so a little bit slower. In fact, if I lowered this even further, say 250 Hertz and 251 Hertz, now the wave envelope should pass by just once a second. The slower those beats come, the closer to being in tune with each other those two frequencies are. The faster they come, the more out of tune they are with each other. So given that, let's take a quick look at an example of this. J Random Troll forms his own rock band. He calls them the Torque Machines. He's getting ready for a big show, but he forgot his tuner. However, he travels everywhere with his handy tuning fork, so he strikes that fork and he plays a corresponding string that should have the same frequency. He hears 3 beats per second. He then tightens that string up a little bit and tries it again. Then he hears 2 beats per second. If his strings have a length of 76.5 centimeters, what was the string's frequency before he tightened it? And what is the velocity of the wave on the string before he tightened it? All right, the beat frequency is simply the difference between the two source frequencies. I know that the tuning fork was tuned to 523.25 Hertz, and I know the beat frequency before he tightened it was 3 Hertz. But here's the problem. Since this is an absolute value, there are 2 possibilities for F2 that'll give me a value of 3. So it's going to be either 520 or 526. Now, which one is it? All right, well, let's go back and look at the rest of the wording of this problem. He tightens the string, and then he hears 2 beats per second. When you hear fewer beats per second, you know that you're getting closer to being in tune. So what effect would tightening the string have on its frequency? Well, one thing that I know about waves on a string is this. The velocity of the wave on a string is the square root of the tension over the linear mass density. That means as the tension increases, the velocity increases. Another thing that I know about waves in general is V equals lambda F. Since his guitar string has a fixed length, the wavelength of the standing wave that's fitting on it isn't going to change. So as the velocity goes up, the frequency goes up as well. So that tells me as he tightens the string, the frequency goes up. And when the frequency went up, it got closer to his goal of 523.25 hertz. Well, if he had started at 526, and then he tightened it, he'd be getting farther away from his goal, so the beats would come more often, not less. That means F2 has to have been 520.25 hertz before he tightened it. What was the velocity of the wave on the string before he tightened it? And I can assume that it's in its fundamental mode. Alrighty. Well, on the fundamental mode, the string is locked down on one end, locked down on the other. The first harmonic just takes me from one node over to the next node. And that's it. Since I know the length of his string is 76.5 centimeters, or 0.765 meters, I can set that equal to 1/2 a wavelength. Because in the first harmonic, going from one node to the next spans just half a wavelength. This allows me to solve for my wavelength, and once I have that wavelength, I can just run it to the wave equation that works for every single wave, v equals lambda f. I know my wavelength, and I know my frequency. Multiplying those together, I find my velocity to be about 796 meters per second. And by the way, I could then use this to figure out the tension on the string. Since this is a wave on a string, I can set it equal to the force of tension divided by the linear mass density. All I'd need to know is the mass of the string, and then I can solve for tension. Cool.